One of the main purposes of our project is to solve a problem with satellite imagery, where we believe satellite imagery is key for mapping and monitoring, but large CNNs are often too heavy for drones and satellites to be deployed and be used in real-time scenarios. So our project's goal is to use the knowledge of distillation to compress these models while preserving accuracy, making them suitable for edge devices. For the dataset, we used the Eurostat RGB dataset, which include 27,000 and more images labeled across 10 land use cases. And for the models, we used the ResNet 18 served as a teacher. For the students, we used the Tiny CNN, Extra Tiny CNN, and Super Tiny CNN, ranging from 2.1 million to 28,000 parameters. As for training, we used distillation combined with cross entropy, with a KL divergence of TF 2.1 and alpha 0.7 to train students using the teacher's soft outputs. And we believe that even with just 10-50% of the data, student models were able to maintain solid performance.
Right, so now we can like dive a little bit more into like actual code, and we can walk through like our specific steps. So I think the first step is we began by loading in the Eurostat satellite image dataset using PyTorch's built-in sort of Eurosat class. And then to prepare, we also performed like a custom transform, and then loaded in the correct like validation and training data loaders that we're going to use throughout the rest of the code base. So next up is we are here importing ResNet 18 just from like torchvision.models as our teacher model, and we're using pre-trained as true. So we're loading like pre-trained weights from ImageNet, allowing us to basically better leverage transfer learning. And because ResNet 18 is we need to like specifically output 10 different classes as opposed to the sort of ImageNet like has like far more final classes. We replace the final fully connected layer with an output of 10 classes here, just to like match our current data set. Yeah, and then here we define a training model very similar to the one we saw in class, using like cross entropy loss, back propagating, and then using the atom optimizer. And then here, just like in class, we are actually training the model, and then here we can see like we get a pretty high accuracy on the training data. But what's more interesting here is when we begin to do like the distillation, we first define a tiny CNN, which has 2.1 million parameters. And as you can see, this is much smaller than the sort of 11 million parameters of ResNet 18. And so it was really interesting to see how like a much smaller model performed. So after defining that, we went ahead and defined our custom distill loss function. So instead of using like the classic like cross entropy, here we are combining two things. One is a hard loss, which compares like the student prediction to the true labels. This is like a very classic. It's like what we usually use for just training normal CNNs. But here we also define a soft loss. And so this is using KL divergence instead of cross entropy. And this allows us to measure sort of comparing like the student's logits with the teacher's softened logits. And so like this allows the student to learn from sort of like the teacher's outputs as well as like the true labels. So like the teacher's outputs, instead of just like outputting like, oh, this is the one correct class, we can see like the teachers also gave certain probabilities to other classes in the same predictions. And so the student models can better learn from like, oh, like maybe like certain classes are similar, and there's like much richer information as opposed to just like which class is correct. And then here we continue to define just a special training function using our distill loss function. And then, yeah, so then we go ahead and taking our sort of tiny CNN that we defined earlier, we went through the same process of training it, but this time with our special distill loss function. And we get a pretty high accuracy on the training data. And then we reuse the same distill loss function for even tinier models. So to even further optimize for like size and speed in specific scenarios, we have our extra tiny CNN and our super tiny CNN. And for our extra tiny CNN, it comes out to around 530,000 parameters. We repeat the same process, get the accuracy here that we're going to compare later, and then do the same thing with our tiny, super tiny CNN. And this only has 82,000 parameters, which is much smaller than the original 11 million parameter model, and sort of do the same thing here.
So as you can see, this is the result, the accuracy 0.88 of our super tiny model, and compared to our extra tiny model, it actually performs that well comparing the amount of difference in the total parameters. And next step, we also considered a scenario where there might be limited amount of information and data that's available for these such scenarios. And so we looked into how we can use a high yielding performance model with a much smaller size and resource. And so this is basically our shrink dataset function that allows to simulate the low data environments that randomly samples a subset of the training set. And then we basically retrain the model using the cross entropy loss and retrain some of the student models of using the distillation loss functions that we had used before. And this one basically is evaluating kind of the raw accuracy of what had happened. So with the changed data, how does our model perform? And we just do that by dividing the number of corrects with the length of our loaded data set. And so the last part is our way of going through the shrinking and the training loop for all three students are tiny, super tiny, and the smaller models. And so we use what happens if we try with 100% of the data, 50% of the data, 20%, and 10%. And so these are all just how the distillation took place. And as you can see with some of our results, as we decreased the number of data sets, we went from the accuracy closer to, as we've seen right here, to something as low as 0.7, but I think this kind of shows that with smaller data sets, we still have a not bad accuracy shown within the model performances.
Cool, so now we can go a little bit into like the results. So after we did knowledge distillation on different percentages of the data set, right here are the results we found. It's very clear that as like the amount of data that the models are trained on decreases, the accuracy also decreases, and that makes a lot of sense just because the model ends up seeing less of the data that's out there. But what's really interesting is as we decrease like the sizes of the models from like the original Resonant 18 to like all the way down to our super tiny sort of CNN with like 82,000 parameters, we can see the accuracy fall off is not nearly as much as we originally expected. So like 0.97 with 100% with the Resonant 18, and then 0.877 with our 2.1 million parameter model. And it only drops to 0.72, even though the number of parameters is only a fraction of the original 11 million. And this sort of holds true throughout the amount of data that we end up using. So the amount that it drops is pretty consistent, and the drop off from sort of like the larger models to the smaller models, because we're using distillation or knowledge distillation, is not nearly as much as we expected. And I think that's like one of the main takeaways from this project, is that knowledge distillation can really help when so we have like really small models like our super tiny CNN, and when we have like very limited data, so like even like 10% of the original data set, we can get like pretty good results for like the resources that we have. Here we can just see like a graph. So they all kind of follow the same patterns in terms of like as you increase the data set size, the validation accuracy increases. Again, here we can see the drop off in sort of how accurate the models are is much less than we originally expected. So now moving on, we wanted to explore like an extra tidbit in terms of like how can we boost the accuracy of our current like knowledge distillation models, especially like our smaller, weaker models. And so we stumbled upon curriculum learning. And so this is basically the process of identifying the more quote unquote difficult samples. So like you have your teacher model, which you just go through like the regular training process on the original data set. But through this, you can identify sort of specific samples in the data that led to sort of not as confident results in the teacher model. So this means, let's say we have like 10 classes in this case in our scenario, and then the model identifies maybe land use case number one as being sort of 99% correct, and then like maybe like 1% for everything else. That in this case would be considered a quote unquote easy sample because the model like had a very easy time identifying what the correct classification was. But if you had the case where maybe it was like 40% for one class, 10% for another, and then you like split them up among multiple classes, that is what we consider here as a more difficult sample. Just because the original teacher model had a harder time sort of identifying what the actual correct class was, even though you can't see that in the actual results. And we wanted to pair this with knowledge distillation, just because like we felt that maybe the order in which we showed the student models the data, like the order that we showed the data in, would matter more, especially because like the student is relying so much on the teacher and sort of like revealing just the harder data set, the more quote unquote difficult samples first. In this case, would achieve a sort of higher learning rate. And the specific, I guess, theory behind like why this curriculum learning, where you're showing like the more difficult samples first, is better, is because specifically for knowledge distillation, the models are learning a lot from the different relationships between different classes, and not just what the peer classification is in the end. So if a teacher sort of has like multiple classes that they're not too sure about, the student models can learn a lot more from that. So presenting these data points where the students can learn a lot more earlier on can sort of like give them a better understanding of the different classes. And this way, as you present easier samples later on, this would sort of allow the model to have like a better learning experience and hopefully increase the accuracy. And so here we go into sort of the code that does just that. We have our entropy, which in this case is a measurement of how difficult the samples are. So we're taking the raw probabilities and then sort of like multiplying with a log of the probabilities, and this would give us our entropy. So again, the more entropy there is, it means the model had a more difficult time identifying what the actual correct class was. And here we are sort of computing the entropies and going through. And here we are creating our curriculum. In this case, it means we are sort of aggregating the data into different buckets of how difficult they were. And this way we can feed, when we're training the student models, we can feed all the student models specific buckets at a time in order to like sort of control the process in which like the order of the data is presented, which is the whole idea of curriculum learning. And here we have our custom train with curriculum model. This is basically doing a very similar thing as the training sort of loops before, except this time we are giving each student model a specific bucket. So in this case, it would start with the most difficult samples and proceed to like less difficult samples. And then going through different epochs on each of these, and then retraining that model with a different set of, let's say, like less difficult samples, retraining on epochs, and we're doing this multiple times in order to simulate like curriculum learning. Yeah, and so we wanted to sort of like simulate with 50% and 20% of the data, just for just because of compute restrictions. We didn't want this to be running forever, and so we can compare with the original 50% and 20% data used from before. So this is a very similar process as before, except here we're calling train with curriculum, so we're doing the curriculum learning instead. And we do this for all of our models, including the 3 different small CNNs. So here we have our data and our results. So after doing all the curriculum learning, we see our final results are here. So we only have the 50 and 20% to compare with the original sort of like fractional data sets without the curriculum learning. And what's really interesting is that we see for our larger models, so on the left here, so with like our medium CNN, extra tiny CNN, with the larger data sets, so 50% in this case, it does end up performing better. So we have a 0.84 accuracy on the validation data set for the medium CNN and a 0.83 on the extra tiny. And then if we scroll up to our original fractional and we look at the 50% for the medium and tiny, both of those numbers are bigger than this, meaning that our curriculum learning did in fact improve the accuracy of our models. But as we sort of go to our super tiny CNN, so a much smaller CNN in this case, with 50% as 0.64 accuracy, and if we compare up here, it actually ends up performing worse than our super tiny CNN without using curriculum learning. And if we keep looking at the results, this seems to be a general trend. So our super tiny CNN with curriculum learning does not end up outperforming the super tiny CNN without curriculum learning. So in general, just like smaller models don't seem to perform as well with this curriculum learning. Also with it decreasing sizes of data, so we have our medium CNN for 0.79 with 20% of the data set and our extra tiny CNN with 0.76. But if we scroll up to our results here, and 20% is 0.77 and 0.76 for medium and extra tiny respectively. The improvement is not nearly as drastic as our 50% amount of the data set for the medium and extra tiny CNN. So in general, the trend that we're seeing is as the size of the model decreases, the effect of the curriculum learning also decreases, and in some cases for the super tiny CNN actually decreases the accuracy of the model. And also, as we use less and less data of the actual like data training set or training data set, the effect of curriculum learning also decreases, which is really interesting. And here is just another graph that we had. Yeah. And so in general, with this project, we sort of explored knowledge distillation, and we found that with knowledge distillation, much smaller models can perform exceedingly well, even though they're much smaller than their teacher models. In addition, we played around with using less data, and we also found that knowledge distillation can sort of heavily improve the performance of smaller models with less data as well. And lastly, we explored curriculum learning, which we found that interestingly, with smaller models, it has a less effect and with less data as well. But with our medium CNN seen here, with like 50% of the data, it still had a pretty significant impact and improvement on the overall accuracy.